Swayam Prabha. Digital India. Educated India.
In the previous lecture we were discussing about the exact solution or analytical solution of a pressure driven fully developed flow through a rectangular channel. Now we will continue with that. So just to recapitulate, this is the cross section of the rectangular channel. We set up our y axis and z axis like this, and the dimensions of the faces are A and B. We basically split this problem into two problems. In one case the problem is like a flow through a parallel plate channel problem, which we had already solved, and in the later case and in the second problem we are basically interested to solve for this problem. This is the second problem. We will keep a note of the boundary conditions on one side of the board, because we have to use the boundary conditions for solving the problem. So at y is equal to 0, del u2 del y is equal to 0, at y is equal to a by 2, u2 is equal to 0, at z is equal to 0, del u2 del z equal to 0, at z is equal to b by 2, at z is equal to b by 2, u2 is equal to minus u1, which is a function of y. This function of y is obtained by solving the parallel plate problem. Okay. Now this is a problem where the governing equation is homogeneous and 3 of the 4 boundary conditions are homogeneous. So we can go for the separation of variables. So we sort a solution of the form u is equal to a function of y into a function of z. Remember that method of separation of variables is one possible way by which you can convert a PDE to a ODE, that is a partial differential equation to an ordinary differential equation, for which maybe more convenient analytical solutions can be obtained as compared to the original partial differential equation. So that means you will get from this equation f double dash g plus g double dash f is equal to 0, and f double dash by f is equal to minus g double dash by g is equal to, yesterday in the previous lecture we discussed that this has to be a negative constant to satisfy the boundary condition. So that is equal to minus lambda square say. So if that be the case, then you have one equation which is f double dash is plus lambda square f equal to 0. So, f double dash plus lambda square f is equal to 0. What it means? What are the solutions of this? Sine and cos. So, f is equal to say C1 sine lambda y plus C2 cos lambda y. Right. Similarly, for G you have G double dash minus lambda square G is equal to 0. So, the solution is e to the power plus lambda z and e to the power minus lambda z, the linear combination of that. So, that we can equivalently write as a combination of cos hyperbolic and sine hyperbolic, because cos hyperbolic and sine hyperbolic is again a linear combination of exponential plus and exponential minus. So, G is equal to say C3 sin h lambda z plus C4 cos h lambda z. Okay. So, the solution is the product Fg, but we have to see whether that is the general solution or not. We will take up this issue in a moment, but first let us apply the boundary conditions to in an attempt to get the 4 constants. So, first let us appeal to the boundary condition that at y equal to 0 del u2 del y equal to 0. At y equal to 0 del u2 del y equal to 0 means basically df dy equal to 0, because in u to f is the function of y. So, df dy equal to 0 means when you differentiate this with respect to y, sine will become cos and cos will become sine, or with plus minus sign, I am not bringing that into the picture. So, then this coefficient of C1 when it is df dy, this will be cos and coefficient of C2 will be sine. So, at y equal to 0 the sine will be automatically 0. So, to make this 0 at y equal to 0 you must have C1 equal to 0. So, this boundary condition gives, let us write this in a box, C1 equal to 0. Similarly, let us consider the third boundary condition. At z is equal to 0 del u2 del z equal to 0, that means dg dz equal to 0. So, when you make dg dz, sin h will become cos h and cos h will become sin h, and by the same logic you will have C3 equal to 0. Okay. So, that means you get f into g. Now, you have these two terms which are underlined here are 0. So, you have f into g is equal to C2 C4 cos lambda y cos h lambda z. This C2 C4 let us call it A. A new constant. Now, you have at y equal to a by 2 u2 equal to 0. So, we apply the third boundary condition, second boundary condition. At y equal to a by 2 u2 equal to 0, that means cos lambda a by 2 is equal to 0. What does it mean? It means lambda a by 2 is equal to what? Odd multiple of pi by 2, 2n plus 1 pi by 2. So, let us write it in a bit of a more elaborate way here. So, you will get lambda is equal to 2n plus 1 into pi by a, right. So, how many possible values of n lambda are there? If you have infinite number of possible values of n, then for each value of n there will be a value of lambda, and see, because it is a linear differential equation, for each value of lambda, if this is the solution, then the general solution is the summation of the solution for all possible values of lambda, right. So, instead of writing the solution in this way, we will write u2 is equal to summation of a n cos lambda n y cos h lambda n z, right. The reason is pretty clear, that for each value of n you have a corresponding solution. The resultant solution is a linear superposition of all these solutions, because the governing differential equation is linear. Okay. So, then the only task that remains is the determination of a n, and the only condition that remains to be used is the fourth boundary condition. So, we will try to make use of the fourth boundary condition for determining a n. To determine a n, let us consider that equation f double dash plus lambda square f is equal to 0. So, this is true for all values of n. So, we can write with f equal to f n, lambda will be equal to lambda n. So, d2 f n dy2 plus lambda n square f n is equal to 0. For all possible lambda n, see lambda n is not, I mean here you cannot substitute all possible values of lambda n, but the lambda n's which satisfy this condition, lambda n is equal to 2n plus 1 into pi by a, only that value of lambda n, not all possible values of lambda n. So, there are only these possible values of lambda n for which you have a non-trivial solution, because you could otherwise argue that if I do not take cos lambda n y as 0, then also I could get a solution, then I would set a n equal to 0, right. Instead of setting cos lambda n y equal to 0, I could have set a n equal to 0 to get the solution, but then if a n becomes 0, u2 becomes trivially 0. So, a n equal to 0 or a equal to 0 is ruled out. That is why for using the boundary condition at y equal to a by 2 u2 equal to 0, we did not set a capital A equal to 0, but cos lambda a by 2 equal to 0. Okay. So, if we had set capital A equal to 0, that could have satisfied this boundary condition, but that could have given rise to a trivial solution u2 equal to 0. u2 equal to 0 means it is a trivial solution, we are interested for a non-trivial solution. So, these possible values of lambda n are the values which are giving rise to non-trivial solution of u2. So, these are called as eigenvalues. Okay. So, you are familiar with eigenvalue problems in linear algebra, like this is a sort of an eigenvalue problem in differential equations. So, meaning is something very similar, that you are getting a non-trivial solution for these values. Now, these corresponding functions f n which correspond to these non-trivial values of lambda n which are obtained from this. So, if you substitute lambda n from lambda n here, you will get some f n, that f n is called as eigenfunction. just the corresponding concept in linear algebra is eigenvector. So, here instead of eigenvector it is a eigenfunction. So, when you so let us proceed with finding out a condition which the eigenfunctions will satisfy for this problem. So, what we do is let us use a different color, we multiply with Fm. M is not equal to n in general, but a special case is there where m is equal to n. So, we multiply this with Fm and integrate. Integrate over y, that is the domain minus 0 to a by 2 here, because our domain is 1/4 of the domain. So, I am not writing the limits here because the limits are not important at this stage, but I mean if you are very particular about it, your limits are 0 to a by 2. Now, what we will do is we will integrate it by parts. So, one of these functions we have to consider the first function and the other function we have to consider the second function. Typically the rule is first function into integral of the second. So, we typically take the higher order derivative as the second function, because we can reduce the order of the derivative by integrating through integration by parts. So, first function, this is first function, this is second function. So, first function into integral of the second minus integral of derivative of first into integral of the second. In the next step what we do, we just do the same thing but swap m and n. So, if we swap n and n, that means if we interchange m and n, what we get? So, f n, just interchange n and m in the above expression. M and n are arbitrary, so you could swap, I mean these are just indices. Okay. Now, let us look into the boundary term. The term in the square bracket is the boundary term. At y equal to a by 2, u2 equal to 0, right. u2 equal to 0 means f equal to 0, and at y equal to 0, del u2 del y equal to 0, that means df dy is equal to 0. So, that means this boundary term becomes 0. See, this is where we require the homogeneity of the boundary condition. Had the boundary conditions not been homogeneous, this boundary term would not be 0, okay, and that would give rise to some sort of complication. You may avoid the complication in a way which I will discuss in a moment, but here this boundary term is 0, this boundary term is 0. Now, you subtract these two equations, this one, say the second one from the first one. So, what you get? If you subtract these two equations, you will see that you will get So, I am writing it at the top, subtracting so this second term gets cancelled. So, lambda n square minus lambda m square integral fn fm dy is equal to 0 from 0 to a by 2. So, what can we conclude from here? What can we conclude? If this is 0, then to generalize, integral fn fm dy is equal to 0 if m is not equal to n, right, because if m is not equal to n, this term is non-zero in general. So, this has to be 0 to make it 0, but if m is equal to n, then that is not necessary. So, this is not equal to 0 if m equal to n, right. This is called as orthogonality condition. So, remember, see, I will give you a little bit of qualitative perspective that why out of so many names it is called as orthogonality condition. See, usually we are familiar from our school level studies, we are familiar with the orthogonality condition in terms of orthogonalities of vectors. Two directions, if they are orthogonal or perpendicular, we say that that's a situation with orthogonality of vectors. Now, here we are not talking about orthogonality of vectors, we are talking about orthogonality of functions. So, what is basically happening here, that in the function space, if you see, when you write orthogonality, that means what? Orthogonality means you have, if you have two vectors which are orthogonal to each other, forget about functions, just take an example of a vector. If two vectors are perpendicular to each other, then what is their dot product? Dot product is 0, right. Dot product means what? Dot product means one component of this vector multiplied with the corresponding component of the other vector, and that is summed up for all components. So, here instead of the vector components being multiplied, it is a functions being multiplied. So, it is a special case of something called as inner product of the functions. So, let us not get into more details of the functional theory here, because our objective is to solve this fluid mechanics problem, and we will like proceed with this. But now let us look into, see, many times we say that for method of separation of variable to work, we require the some of the boundary conditions to be homogeneous, and you can see that while deriving this orthogonality condition, it is clear that why we require the boundary conditions to be homogeneous, so that these boundary terms are absent. Now, in one way, even if one of the boundary conditions was inhomogeneous, it could be possible that this is cancelled by this while subtracting by some way or the other, then also it will work. So, somehow this boundary term has to be cancelled when you subtract. So, whether you require or what kind of boundary condition you require, it is up to you to decide, but mathematically these two terms should cancel. I mean, either individual terms are trivially 0, or if they are not trivially 0, when you subtract one from the other, that should be cancelled. So, that will give rise to this orthogonality condition. Now, why this orthogonality condition is important for solving the problem using the separation of variables method? Let us look here. So, in this expression you have a summation. So, it is possible that to calculate this you require to evaluate a large number of terms, but if you now multiply this with am fm, this is fn, if you now multiply this with fm and integrate both sides,